Welcome, everyone. My name's James Wormold. I'm a staff writer here at Europa Science, publisher of Imaging and Machine Vision Europe. So in today's Visionaries Webcast, we'll be talking about 3D imaging and how the associated technologies and platforms are adding a new dimension to industrial inspection. Helping us to square up to the subject will be two industry leaders who will tell us why it's best to think inside the box. These are Adrian Kruse, a PhD student at the Swedish University of Applied Sciences, and Steve Harris, who's Senior Director of Marketing in the Industrial and Commercial Sensing Division at onsemi. Welcome, gentlemen. By the way, I should point out, thanks, that this webcast, alongside others in the Visionary series, will be available on demand afterwards on the Imaging and Machine Vision Europe website for 12 months. So in case you wanted to recap any of the information, you can go there. So moving on to today's discussion on 3D imaging and its industrial applications, we'll begin with a couple of short presentations from our speakers before we dive into some questions. And if you're watching live, there'll be an opportunity to send in your own questions, which can be answered live as well. So please feel free to send them over to us whenever you think of them. So without any further ado, I'll introduce Adrian first, Adrian Kruse, to give his presentation on how he used 3D imaging technologies to estimate the posture of cows.
Thank you very much for the introduction and for the invitation. So, hi everyone. Well, introduction has been done already, so I'll dive in immediately. I will share a couple of visuals with you. Here we are. Brief introduction to give you a bit of context. I'm a PhD student at SLU, Swedish University of Agricultural Sciences, where we work mostly with sustainability, food systems, but a big dimension of that is digitalization of agriculture. And that's where we have some applications of three-dimensional computer vision, and I'll elaborate more on that. About myself, I graduated with an engineering degree, worked a bit with satellite imaging for sugarcane crop monitoring, and shifted on the animal side of things, working with dairy cattle monitoring. So a bit about dairy barns. I think it's not the environment we think of when we think of sensor-based monitoring, and it's very heterogeneous throughout the world, with some farms being still fairly traditional and some farms being extremely modern and sensor-driven. And here are a couple of examples of sensors that are used. So here on the image that you have is a farm in southern Brazil. In the center, you have the milking robots and cows in the waiting areas, the milking robots. In the milking robots, there's a little Lidar sensor that detects the teats to then place the cups at the right spots. So that is one application of 3D vision in dairy barns that is already quite common. As an add-on to the milking robot, you have a time-of-flight camera that catches an image of cows as they exit the milking robot and gives you an estimate of how fat the cow is, the proper term being body condition scoring. Another common sensor, not imaging this time, but accelerometer-based, you can log activity with ear tags. And finally, regular cameras, RGB, from which we can infer 3D pose, which is what I'll be presenting right now. I'll give you a brief overview of the technology through a short video. Before I place the play button, I want to really explain to you clearly what you're seeing. So on top, on the upper part of the image, you have 4 synchronized frames from regular RGB cameras. On each frame, we detect the individual cows, and then we use pose estimation to detect specific anatomical landmarks. And then that's where the magic happens, because we know where the lines of sight of the cameras intersect. we're able to match the cows in 3 dimensions, and that's what you get on the image at the bottom. It's the digitalized version in 3D of the different location of these key points on 3 different cows. I will no. There we go. I'll press play. I want you to focus on the blue cow because she will be lying down, and that's one of the important movements that we look at. You can also notice that the tracking is not optimal on the legs, but the back line is very stable. That's what we're interested in. So the cow just lied down, and that's actually a very important motion because if cows are not comfortable in the cubicles, they might spend less time lying down, which is both a production issue because more time standing up, more energy expenditure towards standing and less energy expenditure towards producing milk, but also a welfare issue because they don't have comfortable lying spots. So a couple of examples of applications of 3D vision in dairy barns. Locomotor health, lameness is a huge issue in dairy herds, and tracking the displacement of the anatomical features, as the cows move can help us quantify and detect lameness and abnormal posture transitions as I'm working on, but also abnormally long standing bouts. And finally, with the lengthy tracking of dairy cows' position in space, we can also get a feeling of their behavior and use that as welfare indicators. Thank you. That was my short introduction of the technology we're working with. And yeah, I'm looking forward to talking more about it in detail later on.
That's great. Thank you, Adrian. That's a great example of how the technology can be used outside some of the usual industrial applications that you usually think of when you think of imaging technologies. Now, Steve, if you're ready with your slides, with your presentation, take it away.
Absolutely. Yeah, so thank you again. So maybe just a very quick introduction of myself. Steve Harrison, I'm the Senior Director of Marketing for the Industrial and Commercial Sensing Division. It's a part of our image sensor group at onsemi. We have 2 different divisions. We have one focused on automotive and then one focused for industrial and commercial. I have been personally doing imaging now for about 15 years, primarily just in the CMOS, visible CMOS image sensor spectrum. But today, obviously, I'll be talking to you about 3D imaging and depth and some interesting things that are going on there. So just a very quick introduction to onsemi. onsemi is a big global corporation, about 8.3 billion in revenue. Depending on how the stock is doing, $35 billion market cap, somewhere in there. Interestingly enough, we ship 50 billion units a year. That's almost 1 billion devices a week. So we're very much operationally focused. That's not necessarily just image sensors, though. That's a lot of broad range devices across a lot of different applications. And then the 2 focused areas for the company, and of course, I'll be talking about the second one here, but is really power and sensing. And really adding intelligence to that, specifically, actually, as we talk about 3D depth here, we will be talking about some of the intelligence that we're bringing on the sensing side. And then for our heritage in imaging, actually, so the onsemi image sensor group, the DNA is really almost dates back to the kind of heritage of digital imaging and CMOS image sensing. So you can see through a series of acquisitions here through Kodak, IMEC, NASA's Jet Propulsion Laboratories, and Aptina. That's actually where I came in onsemi. Sentel, which brings in Lidar and DTOF. And then very recently, actually extremely excited about this acquisition is Sphere Vision Systems and expanding our spectrum into the shortwave infrared. And really quickly here, I'll just touch on the different types of devices that we have. And I think this actually gives us a really good perspective on kind of the 3D imaging and machine vision landscape, is that we have a lot of different types of CMOS image sensors and depth detection. So Oftentimes, you'll see global shutter image sensors used in stereo imaging for, basically precise timing, I would say, and alignment between the multiple different image sensors. So you'll see that again in 3D. You'll actually see those sensors as well in structured lighting applications for depth. We have rolling shutter sensors, of course. We have sensors that are focused on extremely high dynamic range. And then from the depth side, really just the sensor itself actually doing the depth. We have both direct time of flight and indirect time of flight. My focus is more on the indirect time of flight. But between all of these different sensors and capabilities that we have, I think, it gives us a really good perspective on the whole landscape with respect to 3D imaging. And I mentioned here, maybe I'll talk a little bit just about indirect time of flight. I think this is a technology that still has a lot of room for growth, and we've seen some of the other technologies out there already. But there have been some limitations, actually, specifically with indirect time of flight that have prevented it from getting adopted. First off, it's traditionally not been all that great with motion. So if you have fast moving objects, you could create artifacts and you don't quite get accurate depth. Specifically to, resolutions have been smaller. There's a lot of data intensive processing that needs to happen there. And because of that, it sometimes limits the actual resolution of the sensing system. You get sometimes an addition of cost and space due to some of the complex processing that I'd mentioned as well. That complex processing requires not only bandwidth and the cost through a device, but also you need other components potentially to take up space in the device. And then last but not least, I think is one of the more critical areas too for ITOF limitations, and that's depth and accuracy. So very quickly here, my last slide. Just want to introduce a device that we're releasing and sampling currently that is a smart ITOF device. Again, going back to kind of that intelligence phrase. So the first thing that I talked about was motion artifacts. A lot of the motion artifacts that you see in indirect time of flight are created from the fact that you're capturing multiple different phases to calculate depth. And as you're doing that, you're storing that in memory. You're outputting it likely to a processor, so there's overhead associated with that. And then typically these are based on rolling shutter sensors, which have inherently problems with motion. So motion's been an issue. We get around that by using global shutter technology, and we do all of the storage of the phases locally and processing right on board. So there are literally no motion artifacts with our device. In terms of resolution and accuracy, again, because we're actually integrating a lot of that depth in the storage and the processing on the actual system itself. What that means is that we can enable higher resolution because you don't need such external data intensive processing and interfaces. With that integration, you also get the small cost and size. You don't need an external FPGA, or you don't need a dedicated discrete chip to calculate depth. And then last but not least, what I think is really unique here is the fact that we're using the global shutter technology and multiple different frequencies in order to really gain better depth and accuracy. The global shutter technology means that you can align the entire array exposure at the same time as the pixel. And if you do that for a very short period of time, what you're effectively doing is you're actually eliminating IR light, either from ambient sources internally or more stringently, I would say, is outdoors. So we believe that we have a device right now, I think, that overcomes a lot of these obstacles that ITOF has had in getting adoption within the industry. And then, of course, last but not least, development too is another critical element here. And by providing tools that are reference designs, that are very practical for certain types of applications, and good software that helps in the terms of calibration. These are all things that we believe will enhance the ITOF within our inspection systems, and therefore increase the adoption. So having said that, I'm really excited to talk a Q&A here about all the different types of technologies. We're not just focused on one. I just wanted to kind of note this one particular here because I think this is something that you'll see coming soon, and hopefully can really enhance the adoption of ITOF within quite a few of the inspection industries. So with that, I'll turn it back over, and looking forward to the Q&A portion of this.
Thank you, Steve. Thanks for the presentation there. Those are some impressive numbers posted by Onsemi that is showing the wide number of areas that you're involved in. So there's, like you said, there's a lot to talk about. So moving on to the discussion part of the webcast, and I'll remind anyone watching as well that it's possible to send in any questions that they've got about the presentations or about any of the subjects that we cover. But let's talk about the specific techniques and the technologies that each of you use to inspect samples surrounding 3D imaging. So, I mean, Adrian, if you could start off, tell us about why you chose the specific 3D imaging equipment that you chose for the research project there.
Yes, gladly, and thank you. Before getting started about that, just about the term sampling, I think one of the difference that we have in dairy production is that we're really focused on the cow, even though the product is the milk. And although we take milk samples, we want to have, we want to know how every single cow is doing, and not necessarily a sample of the cows, because it's not representative. So in that sense, that does drive the sensor choice. In our case, I say we, but so the project is in collaboration with Sony Nordic, and they're behind the software. And their idea was that a hardware that would be able to cover as much as possible of the barn is what we needed, because that way we would be able to see all, or at least the vast majority of the cows. We went with regular RGB surveillance cameras, CCTV cameras. And another, I'd say, constraint that we have is farm internet bandwidth, and that limits how much we can download between sites. And it means that a lot of processing has to be done on site. So a sensor that limits the that has quite a low data throughput is also a requirement in that case. And so I think that those are elements that that led to the choice of regular RGB cameras, the images of which are then processed to generate 3D.
Right, and Steve, from your point of view, what are the specific aspects of 3D imaging that you think make it suitable for semiconductor manufacturing and inspection there?
Yeah. So semiconductor manufacturing, of course, because we're a semiconductor company, semiconductor manufacturing and inspection, traditionally from the semiconductor wafer perspective, we've actually utilized more shortwave and infrared type lighting to actually to do visual inspection. Having said that, image sensors themselves actually are very complex devices. You have many times multiple different wafers that are hybrid bonded together. You have many different layers of the actual device itself, between the color filter array, the micro lens. And then even on top of that, as you start to package it, you've got cover glass. Now, anywhere within that complex scheme there of different layers and packaging, we can have defects. A lot of that right now is actually done through visual imaging. And of course, as we all know, visual imaging and just 2D imaging also has its drawbacks. Maybe defects in packages. We use a lot of visual imaging. I think that's because probably there's been inherent limitations with some depth techniques that actually we're overcoming right now. So I actually see that as a future technology that we'll be using in semiconductor inspection, not so much currently. And then certainly, I think a lot of our devices that we're actually creating can help in our own inspection of our devices, and we actually find that happening quite a bit through our customers, our mutual customers.
Right, and moving on, So Adrian, I think you said that you either previously or you also use accelerometers for inspection purposes. Where do you think the kind of line where the use of accelerometers stops in terms of what they're able to do, and 3D imaging can kind of pick it up?
Right. Yeah, there's absolutely a bit of a shift in the technologies being used. In research, indeed, traditionally, accelerometers are used to assess cow behaviors. They're very good for some specific behaviors. The limitation is that you need an accelerometer on every single individual. You need to go and blip them at a regular frequency to extract the data from them. So the larger the herd becomes, the more labor requirements you have to use accelerometers for the research. Whereas computer vision in 3D through fusion of 2D sources is, from my experience, more easily to scale in a barn environment. So I think that's one of the advantages. It's the scalability, and also the fact that once the system is installed, you don't have to go back to it.
Right. Okay. Thanks. And in terms of changes, Steve, then, in terms of changes that you had to make during the process, are there any changes that you had to make to your equipment to optimize efficiency or the accuracy of inspection, maybe?
Yeah, absolutely. And I would say from our perspective, certainly there are equipment aspects to it. I'll talk a little bit about that, but I think a lot of it also is maybe more on the technology side that we're actually using for the implementation. So starting off with the equipment side of things, if we're doing indirect time of flight, using VCSELs, vertical cavity surface emitting lasers that are very precise in terms of their frequency and also have high power is really critical for us. That the tighter the frequency, basically, the more that we can align to that when we receive the light. And basically, by doing that too, you're effectively canceling out a lot of ambient noise that's coming from sunlight or coming from other lighting sources. So from an equipment perspective, I would say having high quality VCSELs is critically important. Now, from a technology perspective, I think this is where there's been a really big difference here in how we're approaching things, which is that a lot of indirect time of flight previously had been based on rolling shutter sensors. And rolling shutter sensors are in a mode where you're basically exposing a row of pixels and reading it out, exposing a row of pixels and reading it out. You're continually doing that throughout the array. But as a byproduct of that now, you may need to leave on that VCSEL for a longer period of time to make sure that all of those rows are exposed. And in doing so, you may be introducing more IR noise. So that's one critical element, is really changing the pixel structure from a rolling shutter architecture to a global shutter architecture. And then secondly, is more on the component side of integration. So as I had mentioned before, these image sensors now, CMOS image sensors, are based on hybrid stacked processes. And so you have a layer that's literally just for pixels, and the layer beneath that actually sitting for all of the digital logic and other circuitry. Now, that layer sitting beneath it generally tends to be the same size as the pixel array above it. And sometimes as a result of that, you actually get extra space to work with. And one of the things that we've done is we've actually integrated some of that really intense data intense depth processing into the actual sensor. And one, that benefits the throughput. You're not having to output multiple different phases to another processor. So an example of a 1 megapixel image, effectively it turns kind of into a 4 megapixel because you have four different phases. Or if you want more frequencies, even more than that, right? So your data is really intense. Then you have to have an external processor or a very complex processor that's able to do all of those calculations. Whereas we can just integrate it into our device and output it from that device. Now we can give data intensity and data coordinates. Oh, by the way, we can actually also give the image as well. So I think from our perspective, It's one, yes, about the components and about the equipment, but two, it's also about the different types of technology that we're utilizing as well to improve the overall system.
Okay, and when you're integrating a new technology such as 3D imaging to any kind of system, well, when you're integrating any new technology to a new system, things don't always go perfectly first time round. So, I mean, Steve, are there any challenges that you could tell us about that you faced when it came to developing the system?
Yeah, quite a bit. And, it really, a lot of it goes down to maybe the calibration and how to specifically calibrate the sensors and the optics, et cetera, for a particular application. Every application is unique and requires different optics, could require different, strength of lighting, could require maybe different resolution. So I think for us, that's always the challenge is the ability to calibrate the sensors. But having said that, I think our learning lesson there was to provide better tools to do that, and maybe to provide a lot more kind of off-the-shelf type calibration sensing calibrations for different types of applications. And then from there, we can kind of go on and refine that. So I think that's one of the kind of critical things that we've really learned through the process here is about calibration. The other thing too is that when you're in a system that's doing depth, I talked about ITOF, right? It's a combination of a pixel plus a sensor. If you have multiple different sensors or even different types of sensors, let's say another DTOF sensor that's using same frequencies, sometimes you can get interference between that, and your sensors are maybe not aligning necessarily to the frequency that you've output, or maybe it's picking up noise from other different sources. So another thing too with respect to that is by adding some spread spectrum clocking to our devices, we can kind of eliminate all of the exterior noise sources as a result of multi-camera systems and other types of light. So those are a couple of things that just off the top of my head I can think about that we've integrated for improvement. Calibration techniques and spread spectrum clocking.
Okay, thanks. And Adrian, you were nodding along there to Steve's answer. So was calibration a big problem for you as well? Or?
Yeah, it's an ongoing struggle. Yeah, I really relate to the issue of calibration, and yeah, I absolutely agree. I think that's it's a super important part to get right. It's something that has been challenging for us to get right. I think one of the difficulties that we're working with is the barn environment that's not necessarily meant for placing sensors. And theoretically, when doing 3D fusion of 2D pose estimation, you need two cameras to see the same element. Our experience is that it works best with four. More than that, we start having the more inaccuracies in the line of sight intersections, the more noise we get, but also the fewer cameras, the more risk for occlusion. So we have a fairly uneven coverage depending on the area of the barn, with some central points that are extremely stable, and some corners where we have a lot less accuracy. And getting the calibration right, and in our case, it's finding the intersecting lines of sight is a challenge in those corner areas. So that's, yeah, the main technical challenge. And I think a challenge when it comes to inspection per se and the application is that we're working with living animals. There's a lot of variation between individuals in the behaviors they express, and also how they behave when they have different health issues, for instance. But also the fact that the most severe health issues, which we want to detect or predict as early as possible, are also the rarest ones. And so it's very hard to collect ground truth data to then calibrate the software that interprets the pose data. So yeah, those are the two main challenges for us, and absolutely relates to calibration.
Right. So the term "never work with children or animals" is true for imaging inspection as well. Following on from the challenges, then I guess, and this one goes out to both of you. I mean, anyone can jump in, but how do you go about ensuring the 3D imaging equipment that you use will be fit for purpose before you select it?
I guess I'll take that. Really, in our case, we cover a lot of different applications. We have a lot of different types of devices. I really, for us, I think it is about the history that we've had in the industry, the types of devices, and then what that culminates in is just building a lot of domain knowledge and prior learnings. What works best in certain scenarios, what type of technology works best in different types of scenarios. So I think for us, it's really just a learning experience as we go. And I think we have been able to kind of fit certainly some technologies within certain applications. We have app notes and we have presentations and we have information on different applications that we're going into. So I think for us, having all of these mentioned off the top, a lot of that actually comes from engineers who are working on high volume consumer devices in the 3D space. And it was really just taking their pain points and saying, hey, these are the challenges that we had. We had challenges with motion. We had challenges with depth. We had challenges with interference from other lighting sources. We had challenges with cost and space. All of those things that I'd mentioned kind of up front, those were really things that actually we had learned from prior pain points in customers. So I think it's really just a learning experience. And then, having close intimacy with our customers too, really trying to dig into what the problems are at a very basic and fundamental level and what problems they're trying to solve really helps us, I think, also too, with creating the right device for the customer. And then having a complementary portfolio also means that, let's say that we are trying to force a technology in, and it's just not fitting the application. We kind of have the ability to kind of maybe pivot a little bit and find a different product within learning from their experience on their pain.
Okay, and Adrian, from your point of view, then, when you were completing your study, were you able to consider which solution would be best for your purpose before you brought everything together, or was it a case of kind of suck it and see, or is that kind of what you were talking about accelerometers and then 3D imaging on top of that?
Yeah, in the sense that it is. In a way, it's very prospective. There was some interest both from the university, but also industrial partners, so namely Sony Nordic, who's working on the technology, but also a company called Vexa, who does notably certification for animal production. And yeah, what was noticed is that in increasingly large herds, it's difficult to keep an eye on all individuals, and you have an increased lag time in the detection of sick individuals. And the second one was also for certification. Vexa, that company, does a voluntary welfare certification where they send an assessor on the farm to look at the animals and their behaviors. But that, of course, is done for a couple of hours, a couple of times a year. So it doesn't give this whole picture of how the animals are doing. And they wanted to see if there was a lightweight way to do it with continuous monitoring to get a more complete picture of animal welfare. And yeah, I guess that seeing if it's fit for purpose is, in a way, seeing that we're able to answer those questions, that we are answering questions that were not answerable from the human eye, which is the gold standard still on a lot of farms. the work that we're doing in the cubicles, we're getting a feeling that it is the case because we're able to actually accurately measure displacement of those anatomical features. An alternative way to do that is motion capture, but that's not feasible in a barn. And so we're getting the feeling that this is a technology to do it. There's also someone working on accelerometers, and I don't want to throw them under the bus because I think that what they're doing is also working really well. And the barrier to entry, I think, of 3D computer vision compared to accelerometer is a bit higher. But then also on the welfare and health monitoring, if it's something where we see genuine interest from the industry, thinking that this can deliver value, improve their work with certification, then it'll be the confirmation that the technology is fit for purpose.
Okay, I think and Sony have just provided they've just written a feature on the Imaging and Machine Vision Europe website about 3D imaging, and kind of what would you say would be their involvement? How crucial was their involvement in the project in terms of using the equipment? Or
it was essential in the sense that there would be no project if there was no Sony. There would also not be any project. There was no SLU. And I think it's a brilliant collaboration, and it's also, in a sense, the bridging of skills that we needed because they are insanely good at hardware, but also at software. They don't necessarily have this experience of working with cows and knowing what issues we're looking for, what's, in a way, I'll say how farmers think and what delivers value in a dairy barn. So in that sense, I think this collaboration has been extremely rewarding because of this bridge of experience and competence.
Okay, thanks. And Steve, moving on to sort of lens specifications and camera specifications, what particular specifications proved ideal, do you think, for your needs, your inspection needs?
So that is an interesting question right there, because I don't know that there actually is a single ideal specification or lens. I mean, I think it kind of goes back actually to what we were talking about before, and the kind of difficulty in calibration, and also the difficulty in actually choosing a device. So for in our case, literally almost every application requires something different. There are sometimes we can kind of typecast things with a single machine vision camera, but if we do that right, we have to kind of address broader needs. So there are times where we can kind of go after an application with a single camera that maybe that application has a lot of commonality. But going back to it, I think what that also really means is that you need to have a diverse portfolio of solutions. So if somebody comes to onsemi and they have a sensor in mind and a resolution in mind, or they have a different technique of how they want to do depth in mind, and all of a sudden, what they're finding out it's not working right, to be able to work with the same people that understand your problem and be able to provide you a recommendation for a way to improve that problem or to be able to go into a different direction, I think is extremely helpful. So again, it's very rare that I find a scenario that we have one application that will use a common specification, but having the ability to kind of adapt and move and have different kinds of solutions, I think is really helpful.
Okay, thanks. And Adrian, did you, from your side, did you find that you needed any specific lens requirements that you found?
We need the perfect surveillance camera in the sense that we need to cover as much of the barn as possible with as fewer sensors as possible to keep the throughput as low as possible. And at the same time, we want a camera that had low barrel distortion because we need to correct for that to calculate the intersecting lines of sight. Can I do some brand dropping?
Yeah, that's fine. Yeah.
Yeah, we use the G3 Bullet camera from Ubiquiti. It's a surveillance camera, general purpose, and yeah, it's. I don't know if you manufacture sensors for them, Steve, but
my smile might be an indication, but yeah. But you know, I think what Adrian, what I would say, by the way, too, is I think what Adrian is pointing out is almost kind of similar to what I'm saying, right? Like he had a very specific application that may require something completely different than, you know, the way a camera was intended for another different application, right? And so that's why I think there needs to be that kind of adaptability, because like certainly his application is very unique, but there are thousands of different types of applications that are unique as well. So yeah, and certainly the adaptability and kind of having a range of different solutions, resolutions, et cetera, I think is critical, just for the type of application that Adrian is working on.
Right. Thanks. Yeah, that's a good note. So moving on to another topic, another really hot topic, not just in imaging or optics at all, but in every kind of sector, sustainability. It's a hugely important consideration to manage resources, first of all, and therefore costs, but also from a wider environmental point of view. So how can 3D imaging help here with sustainability? And if it can, how can companies, large and small companies, go about managing it efficiently? That's to Steve, maybe.
Yeah, I mean, I mean, I can think of many different ways that 3D imaging enhances a factory inspection line. You're looking at a bunch of different apples coming across it, and you want to see if there's a dent in the apple that maybe you can't acquire from a 2D image due to lighting and other reasons, right? Okay, now, well, if you have a difficulty with the motion, right, and you have to slow down your inspection line, or maybe even stop your inspection line to take a picture, you've decreased your overall throughput, right? So, so that's certainly, you know, one that comes to mind. It's just making systems a lot more efficient. I would also say too that, you know, just from even our own perspective, developing at a kind of a family level, meaning that you have kind of a similar type device, but you provide different options, allows us to utilize our designers more efficiently, of course, and also allows our customers to be able to choose differently, I would say, between sensors, but also, you know, those sensors share a commonality, so they're not going to have to relearn a brand new architecture and a brand new sensor. The other thing I would even from our perspective, is that there are some technologies that have similarities. For example, your basic 2D image sensor is the same kind of as your iToF sensor, maybe with just some different optics, right? So leveraging technologies that you have for different types of applications also means that you're optimally using resources. So I think from a you know, an end user scenario and making customer systems more efficient, I think there's an element there of sustainability. From an element of our own design and how we do things, I think there's an element of sustainability. There are things that actually come across to us that we don't even think about, that are challenges. One, for example, is that, you know, self-checkout has become all the rage, and most places now have self-checkout. Of course, what comes along with self-checkout is theft. And, you know, people find ways to game the system. For example, somebody may take a barcode off of a box that's really, really cheap and slap it onto a box for a device that's extremely expensive, swipe it, everything looks good, right? The more information you can provide, including depth, right, the more effective that system can be in preventing theft. So, you know, I just see a lot of different uses from a customer standpoint, making itself more efficient, preventing things like theft. And then even in our own development process, I think we can use better resources, have better resource utilization, and better technology leveraging internally as well. Kind of hitting both aspects there, market and internally.
Yeah, thanks, Steve. That's a good example of another alternative application as well. And Adrian, is there anything that you wanted to add on the sustainability aspect, maybe?
Yeah, sure thing. I definitely join you, Steve, on if the efficiency aspect. And I think particularly dairy farming is often pointed out as being responsible for a lot of emissions, a lot of environmental impacts. And to be fair, it is. And so anything that can improve the efficiency of dairy production in a way has a positive impact on sustainability. And I do acknowledge that it is a particularly productivity-oriented take on sustainability. But to put it into example, if cows will consume feed that have an impact when they're produced, and cows will also generate emissions of methane. When cows get sick, they will produce a lot less milk. They will still eat and emit, albeit a bit less. But so the emissions per unit of milk produced, per unit of human foods produced, increases. And so by having sensor systems that are able to detect and even better predict which cows are at risk of diseases, you can contribute to having farms be a lot more efficient. So that's one point. Another take, and I know it's a bit debated whether that is sustainability or not, but it's animal welfare. Along the same lines of early detection of diseases, the earlier you're able to detect that something's wrong with an animal, the earlier you're able to treat it. And so the less time it spends in a miserable state. So sorry to use basic words, but that's one aspect of it. But there's also the aspect of what researchers are starting to call positive welfare, which is how do we know that a cow is living a life worth living? And there's a lot of behavior signs of the emotional states of cows. And a system like the one that we're using that's able to continuously track cows can hopefully both provide the data to better understand how cows in positive, effective states behave, but also in production setting get measurements of how those behaviors are being expressed, and are we having cows expressing behaviors indicating positive or negative emotional states. And I think that's a huge one behind this 3D post technology in dairy barns.
Yeah, no, I agree. I think it's an important consideration, maybe not as impactful as other kind of direct sustainability uses, but it all counts. It all kind of adds up. And finally, I think the last question we've got time for, if we can squeeze it in. We've got a lot of integrators and end users who are watching and listening in. If there's one kind of key bit of advice that you could give them about how to get the best out of 3D imaging for inspection, what might that be? Maybe Steve.
Yeah, I think it's really important to start basic. What is it that you are at the fundamental level truly trying to achieve? And start from that and kind of build upwards. So, okay, now I want to be able to detect a dent, like I was saying, in an apple moving across an assembly line, and then start building up from there. Okay, what kind of lighting conditions am I dealing with? Is it going to be the same system in multiple different warehouses where lightings are going to change? Is it going to be outdoors, like in Adrian's case, right? If it's outdoors, that's a whole unique set of challenges, right? With infrared light coming from the sun, do you need a visible system? Does it get extremely dark, right? Do you need low light? So I would say if you start from kind of the basic and what am I trying to achieve, and then start building up and start thinking about, okay, here are the different lighting conditions that I have and the kind of circumstances that I'm going to be under. You can really then start figuring out and kind of tailoring your system to what type of device you need and what 3D imaging is going to work best for your usage case. And oftentimes what I'll see is that sometimes people will just kind of pigeonhole themselves. Maybe they're familiar with 3D ITOF, and maybe they're familiar with stereo imaging. Maybe they've used DTOF in the past, right? And they pigeonhole themselves in that because they've got that expertise and they drive so far, but to find out that, you know what, it's just not going to work. So I would say start broad, be open-minded, define your conditions on what you want to achieve, define the lighting conditions that you're going to be under, because they're always going to be different. And then really start to figure out, okay, what's the best solution for me? And again, there are many different types of solutions out there. ITOF has just, like we said, gone through a recent improvement with our devices. So don't pigeonhole yourself. Start broad, think about your specific needs, and really start looking at your conditions, and then start trying to figure out what technology you need. And I think that's kind of a good way of approaching it.
Yeah, thanks. That's good advice. And Adrian, is there any insights that you've learned from your experience which you could advise people, anyone who's listening and thinking that they are about to undertake a similar kind of project, a similar kind of choice?
Yeah, for sure. I would say be ready to scale up and that might come very much from personal experience, but we started with, I think, 5 cameras on a very limited area, and we thought that this would be it because it was development. And really quickly, we were working with 35 cameras for the same pen. And at the beginning, each additional camera was a huge, was quite labor intensive in terms of installation. When we realized that we kept continuing to scale up, we had the electrician intervene, put some switches directly in the pen over the cows, made a way more flexible system from which we can very easily scale up. And I think if we had done that from the very start, we would have made progress a lot faster.
Yeah, that's another good point about the flexibility of your system, is being prepared to not just change the types of equipment that you use, but the scale as well, like you say. That's perfect.
Flexibility was a good point.
I agree.
Well, that's just about all we've got time for today at the moment. So I'd just like to thank both of our guests again, Adrian and Steve, for talking with us about your use of 3D imaging at your applications and your views on the technology. This webcast will be available on demand in the webcast section of the website, along with previous recordings from the past 12 months. So please check that out. There's just time to mention the next webcast in the Visionary series will be live on the 19th of February. We'll be talking to guest speakers from Edmund Optics and Gold about how to choose the perfect application-specific lens design. So I'm looking forward to doing that one. But until then, depending on which part of the world you're watching from, good night, good afternoon, or have a great rest of the day. Thank you.
All right. Thank you. Thank you, James, for hosting as well.
Thank you.
Really enjoyed it. Thank you, Adrian. Cheers.